So today I'm going to talk about work with Alison Etheridge, and it's also quite closely related to the book that Raphael Florian talked about this morning. So it's about a population made up of two genetic types, one of which has an evolutionary advantage, and to understand how the advantageous type spreads through the population and what the genealogy is. So before I talk about the actual biology for this project, I want to say a bit about a slightly simpler example. So throughout the tour, we're going to have call our two different genetic types, little a and little a. And for this example, we're going to be just thinking about a haploid population, a population in which each individual carries just one copy of each. So each individual, either a type little a or a type. And we're going to have a small positive parameter S, which we'll call the selection parameter. And we'll say that individuals have these relative fitnesses. So type little a individuals have fitness 1, and type A individuals have a slightly higher fitness of 1 plus S. And we're going to suppose that the population is spatially structured, and throughout the populations are living in one spatial dimension. So there is sort of two questions to ask about all of this population. So the first is, how does the advantageous type capital A set in space through the population? So maybe the most cool way to model the relation would be to use a deterministic PDE, the Fisher-K population. So here U of T and X represent the proportion of type capital A population. Oh, you've got an echo.
Right. So how does the advantageous type capital A spread through the population? So we could model it using the Fisher-KPP equation, where we have U of T and X represents the proportion of type capital A in the population at location X and at time T. And du by dt is given by Laplacian of U plus a nonlinear term. So the Laplacian term reflects that individuals in the population move around diffusively in space, and the nonlinear term reflects the difference in relative fitnesses in the population. And if you, it turns out that if you take an initial condition for this equation that's front-like, then it converges to a traveling wave, a particular traveling wave solution of the equation. So that's roughly how the type capital A spreads out through the population according to this traveling wave. So then the other thing that we'd like to understand is what do genealogies look like? So what I mean by that is if we sample some multiple type capital A individuals from sort of fairly near the front of the advance of this type capital A, and we trace their ancestry backwards in time, then we'll get a coalescent process, because as we trace the ancestral lineages backwards in time, oh, I've just realized I didn't turn my webcam on. As we trace the ancestral lineages backwards in time, then ancestral lineages will coalesce when they have a common ancestor. And it's widely believed that if you take a reasonable model of this population with these fitnesses and with spatial structure, then the genealogy that you should get for a sample of type capital A individuals under a suitable time rescaling should converge to a Bolthausen-Snitline coalescent in the limit of large population density. So that's what are expected to be the answers to these two questions in this simpler case of directional selection. So now I want to tell you about a different selection mechanism, and we're going to ask these two questions again, and the answers are going to be somewhat different. Now we're going to be again having our two genetic types called little a and capital A, But now we're going to be thinking about a diploid population, so a population in which each individual carries 2 copies of each gene. So an individual would be made up of a pair of the genetic types little a and capital A. And we're still going to have a small positive selection parameter S. So first of all, so these blue values are going to change, but first of all, let's just think about the case where the relative fitnesses were like this. And so the advantage in fitness of having one copy of capital A, if that was exactly half the advantage in fitness of having 2 copies of type capital A. So in this case, we would expect the behavior to be essentially the same as in the directional selection case on the previous slide. So what we're going to look at instead is we're going to modify these relative fitnesses. So we're going to have a new parameter gamma, and we'll modify the relative fitnesses so that the advantage of having 1 copy of type capital A is less than half the advantage of having 2 copies. So this is what we're going to do. We're going to have this positive parameter gamma, and then we'll say the relative fitness of type little a individuals is 1, and the relative fitness of little a capital A individuals is 1 plus gamma minus 1 times S. And then for capital A individuals, it's 1 plus 2 gamma S. So you can see that if depending on whether gamma is less than or bigger than 1, then the relative fitness of these little a capital A individuals can either be bigger or smaller than the relative fitness of the little a individuals, but it's always an advantage to have 2 copies of type capital A. And what's also always the case is that any advantage that you get from having 1 copy of type capital A is less than half the advantage that you get from having 2 copies. And this, it turns out to be a mathematically convenient way of parameterizing this situation. And again, we're going to be thinking of a spatially structured population that's living in 1 spatial dimension. So what we were interested in is if we take an individual-based model of this population, then how does the advantageous type capital A spread out in space through the population, and also what do the genealogies look like? So first of all, we need a model. So I'm going to show you the model on the next slide, but on this slide I just want to give some motivation for the model. So at the top of the slide, I'm just reminding you of the relative fitnesses of individuals in the population. So now on this slide, for now, I want us to ignore spatial structure and just think of the whole population as being in 1 place. And let's suppose that the current proportion of type capital A in the population is W. So by that I mean that if we add up all the pairs of types that make up all the individuals, and then we work out what proportion are type capital A of all of those types, then it's W. So if we assume that the population is relatively well mixed, then it should be roughly in Hardy-Weinberg proportions, which means that the proportion of individuals that are capital A should be roughly W squared, and the proportion of little a individuals should be 1 minus W squared, and then the little a capital A should have the remaining proportion of 2W 1 minus W of individuals. And then the way that I want to think of reproduction as happening in the population is that each individual produces a large number of gametes, so reproductive cells that are single types. So capital A individuals will only produce capital A gametes, and little a individuals will only produce little a gametes, and then little a capital A individuals will produce half little a gametes and half capital A gametes. And the way that the relative fitnesses are going to be reflected is that the number of gametes that individuals produce will be in the ratio given by their relative fitnesses. So little a capital A, and capital A individuals will produce numbers of gametes in the ratio 1 to 1 plus gamma minus 1 S to 1 plus 2 gamma S. And then once these gametes have been produced, then they fuse at random to form new individuals. So let's suppose that we pick a single gamete uniformly at random from this large pool of gametes. So what's the probability that, what's the probability that this randomly chosen gamete is a type capital A? So the gamete could have come from a capital A individual, and they have proportion W squared, and they produce a number of gametes proportional to 1 plus 2 gamma S. Or alternatively, the type A gamete could have come from a little a capital A individual, and they have proportion 2W 1 minus W, and half of their gametes are type capital A, and they produce a number of gametes that's proportional to 1 plus gamma minus 1 times S. And then we have to divide by this factor on the bottom to get our proportions to add up to 1. So that's the probability that a gamete is type capital A. So now what we're going to do, just so for the purposes of this motivation for our model, because we're thinking of S as being small, we're going to expand this thing in powers of S, and we're going to ignore the terms which are order of S squared. So if we expand this in powers of S, we can write it in what turns out to be a convenient form. So we can write it as 1 minus gamma plus 1 times S times W, plus gamma S times 2W minus W squared, plus S times 3W squared minus 2W cubed, and then plus order of S squared terms. So now let's let X1, X2, and X3 be IID randomly chosen types from the current population. So by that I mean that each Xi is either little a or capital A, and the probability that an Xi is equal to capital A is W, because that's the proportion of type capital A in the population. So then the probability that the majority of X1, X2, and X3 are capital A is, well, it's the probability that all 3 of them are capital A, which is W cubed, plus the probability that exactly 2 of them are capital A, which is 3W squared times 1 minus W. And that works out as 3W squared minus 2W cubed, which is exactly the same term as this term that we have here. So so I got to saying that the probability that the majority of these 3 IID randomly chosen types are capital A is 3W squared minus 2W cubed, which is this term here. But also if we look at the probability that at least one of these 2 IID types are capital A, well, that's 1 minus the probability that both of them are little a. So it's 1 minus W squared, which comes out as 2W minus W squared. So that's exactly this term here. So what we're actually going to do is, because for our model it's a lot easier to work with just single types rather than individuals being made up of pairs of types. Effectively, in our model, we're never actually going to fuse together the gametes into pairs of types to make individuals. We're just going to work with single types. And the way that we're going to reflect the relative fitness of individuals made up of pairs of types is that we're going to have 3 different types of reproduction event. So first of all, with probability 1 minus gamma plus 1 times S, then we'll just have a neutral reproduction event where the new offspring type will be a type capital A. The new offspring type will just be a uniformly chosen type from the current population, and so it will be type capital A with probability gamma. And then instead we're going to have a selective reproduction event that will happen with probability gamma times S. And in one of these selective events, then we will pick 2 types from the population, and the offspring, the new offspring type will be type capital A if and only if at least one of those 2 types is type capital A. So that will happen with probability 2W minus W squared. And then finally, we'll have another type of event that will happen with probability S. And for those events, we will pick 3 types from the population. And the new offspring type will be type capital A if and only if the majority of those three types are capital A, which will happen with this probability. So that's the way that we're going to reflect relative fitnesses in the model on the next slide. So now I'll show you the model that we actually use. So from now on, we're going to sort of cheat a bit and call something an individual when actually really it's just a single type. So individuals are not going to be pairs of types anymore. So now we're going to have a stepping stone model where we have a fixed number, capital N, of individuals at each site in the integers, and we'll have a scaling parameter, little n, and we'll have a positive constant m. And for each integer site x, then for each I in 1 up to n, then we'll have an independent Poisson process with rate half n squared. So that will turn out later to be a convenient time scaling. And at a point of one of these Poisson processes, we sample an individual. So the individuals at x will be labeled with the numbers 1 up to n, and we will sample an individual uniformly at random from those individuals. And let's say that it has label j. And then, as I said on the last slide, we'll have three different types of event. So with probability 1 minus gamma plus 1 times Sn. So Sn is still our selection parameter, but it now just depends on the scaling parameter n. So with this probability, we just have a neutral reproduction event where the individual with label I dies and is replaced by offspring of the individual with label j. And then instead, with probability gamma times Sn, the individual with label I dies and is replaced by offspring of the individual with label j, if and only if individual j is type capital A. And if not, then nothing happens. So this is a selective event that gives an advantage to the type capital A. And what ends up happening is that after this event, then individual I will be type capital A if and only if at least one of these two individuals just before the event was type capital A. And then finally, with probability Sn, we sample another individual, k, uniformly at random from the individuals at x. And if individuals j and k have the same type, then individual I is replaced by offspring of individual j. And if not, then nothing happens. So for this final event, then individual I will end up as a type capital A if and only if the majority of these three individuals just before the event are type capital A. So that's what happens for reproduction events just at one site. And then we also have some migration events. So for each pair of sites x and y in the integers that are neighboring sites, then for each I and j in 1 up to n, then we have an independent Poisson process. And at a point in this Poisson process with rate mn squared over 2 capital N, and at a point in this Poisson process, the ith individual at x is replaced by offspring of the jth individual at y. And the reason that we have this extra 1 over capital N here compared to this rate here is that we have capital N choices of j for each I here. So this is the model that we're going to work with from now on. So it turns out that to get a non-trivial limit, we want to take Sn, the scaling parameter, to be some constant S0 divided by n squared. And we're also going to suppose that capital N, the number of individuals at a site, is much bigger than the scaling parameter little n. And for convenience, so that some of our coefficients go to 1, we're going to, for the rest of the talk, we're going to take S0 to be equal to 2 and also m to be equal to 2. And we're going to let Pnt of x be the proportion of type capital A at the site x at time t. So that means that out of the capital N individuals at x at time t, there's a proportion Pnt of x which are type capital A. So it turns out that if we scale space by 1 over n, and if you remember, we already effectively scaled time by n squared in the definition of the model, then PNT converges to the solution of a PDE. So if n is very large, then PNT of n times x is roughly u of t in x, where u solves this PDE. So du by dt is Laplacian of u plus two nonlinear terms, and then the initial condition is given by the linear interpolation of the scaled initial condition for Pn. So you can see that the second nonlinear term that we have here is the same as the nonlinear term in the Fisher KPP equation, and then we've also got this extra nonlinear term here. So why would we expect to get this PDE? Well, if you remember from the slide about the motivation, so if W is the proportion of type capital A in the population at some site, then roughly speaking, the expected proportion of offspring which are type capital A, we said should be roughly 1 minus gamma plus 1 Sn times W plus gamma Sn times a nonlinear term in W plus Sn times another nonlinear term in W. And so roughly speaking, the expected change in proportion of type capital A at a reproduction event should be this thing minus W, because a uniformly chosen individual dies in a reproduction event. So if we take W off from this, then we can just remove the first term and take away W from each of these two other terms, which gives us this. And then if we factorize each of those terms, we get gamma Sn times W1 minus W plus Sn times W1 minus W 2W minus 1. So this term here is where the second nonlinear term in the PDE comes from, and then this term here is where the first nonlinear term comes from. So effectively, this first nonlinear term is coming from this, which comes from the events that give advantage to the type that's in the majority, and this nonlinear term comes from this, which comes from the events that give an advantage to the type capital A. So that's where the nonlinear terms come from, and then the Laplacian term comes from the migration events in the model that have a smoothing effect. So that's roughly where the PDE comes from. So what do solutions of the PDE look like? Well, so it turns out that if you start with a front-like initial condition, then solutions of the PDE converge to a particular travelling wave solution. And for gamma bigger than 2, then that travelling wave solution is what's known as a pulled wave, which means that the behaviour is driven by what happens in the tip of the wave. But for gamma between 0 and 2, the relevant travelling wave is a pushed wave, which means that the behaviour is driven by what happens in the bulk of the wave. And we're going to be concentrating on the push wave case from now on. And in that case, the travelling wave has a nice explicit form. So if we let g of x be 1 over 1 plus e to the x, then if u of t and x being g of x minus gamma times t is the travelling wave solution of our PDE. So here I've just put the two nonlinear terms together into one nonlinear term, and this turns out to be the travelling wave solution that solutions with front-like initial conditions converge to. So in the picture, I'm trying to show you roughly what this travelling wave solution looks like. So it has shape g, and it's moving to the right at speed gamma. So that's what solutions of the PDE look like. So now if we go back to the individual based model, so we're going to let mu nt be the rightmost x at which pnt of n times x is at least a half. So under the space scaling by 1 over n, it's the rightmost point at which the majority of the population is type capital A. So it's sort of how far the type capital A has spread at time t. And we're going to refer to that as the position of the random travelling front at time t. So what we can show is that the random travelling front moves to the right at roughly speed gamma, and it has a shape that's roughly given by this explicit function g. So we can show that rigorously in the case where gamma is strictly between 0 and 1. So this is a sort of a rough form of a result that we can prove rigorously. So if gamma is between 0 and 1, and then we want to say that P0n is equal to 1 a long way to the left of the origin, and it's 0 a long way to the right. So we're starting with all type capital A a long way to the left and all type little a long way to the right. And we also have a technical condition that there's some small positive constant b such that the supremum of the difference between P0n of n times x and g of x is at most b. So under these conditions, then if n is large, then with high probability, we can say that if we scale Pnt by 1 over n, then it's very close to g of x minus mu nt, and that's for all x, and for t relatively large, but not crazily large. And then we can also say that if we take mu nt minus mu ns and divide by t minus s, that's very close to gamma for s strictly less than t and s and t not too close together, and both in this time interval. So we've got this random traveling front that's moving to the right at speed roughly gamma, and it has shape roughly g. So we can prove this for gamma less than 1, and the difficulty for gamma greater than or equal to 1 is that the growth rate in the tip is non-negative, by which I mean that if we take a small positive u, then the value of these two nonlinear terms added together is non-negative. And that means that the convergence of PDE solutions to the traveling wave is more delicate, and also means it's harder to control the effective noise in the tip of the wave. So that's roughly why so far we've only proved this for gamma less than 1, and gamma between 0 and 1 is the bistable case. So that's roughly how the advantageous type capital A spreads out in space through the population. But what we also wanted to understand is what do the ancestral lineages look like? Sorry, what does the genealogy look like? So we want to be able to take multiple type capital A individuals and trace their ancestry backwards in time. So to start with, let's just think about a single ancestral lineage. So we're going to take a positive time capital T and a site x in the integers and a little t between 0 and capital T. And let's let zeta n capital T little t of x be the location of the ancestor at time capital T minus little t of a randomly chosen type capital A individual at site x and at time capital T. Or in other words, at time capital T at the site x, I choose a type capital A individual uniformly at random from the individuals at that site at that time, and I trace its ancestry back for a time little t to get to time capital T minus little t. And I ask where in space is this ancestor. So it turns out that if we rescale this location by 1 over n and then recenter it by the position of the random traveling front, then it behaves roughly according to a diffusion. So this result is sort of morally true, and what we actually prove is slightly different. But so if we take a finite constant t0, and if we let capital Tn go to infinity as n goes to infinity, so we're going to sample a type capital A individual at this time capital Tn and at a location xn. So we want xn to be not too far from the front at time capital Tn. So when we rescale xn by 1 over n, we want it to be at most a large constant capital K away from mu n Tn. So in that case, what we can say is that if we take the ancestral lineage of a randomly chosen type capital A individual at xn at time capital Tn, and let the time that we trace it back for, t, vary, if we rescale by 1 over n and then take away the position of the random traveling front at the relevant time, then this process behaves roughly like a diffusion zt, where dzt is, so we've got two drift terms, and then we've got plus square root of 2 dbt, and and where BT is a Brownian motion. So where do these two drift terms come from? Well, for the first one, so the random travelling front is moving to the right forwards in time with speed gamma. And so backwards in time, the random travelling front is moving to the left with speed roughly gamma. So that means that relative to the random travelling front, as you go backwards in time, the ancestral lineage is moving to the right with speed roughly gamma. So that gives us this gamma dt drift term. And then for the other term, so if I'm a type capital A in ancestral lineage, and I've got more type capital A's to the left of me than to the right of me, then I'm more likely to have come from an ancestor that was to the left, where there are more type capital A individuals. And so I'm more likely to get, I'm going to get pulled up the gradient of the travelling wave. And that ends up giving us this second term here. So we've got two competing drift terms, one that is pulling the ancestral lineage into the tip of the wave and one that is pulling it up the gradient of the wave. And it turns out that these two terms, these two competing effects balance out in the case where gamma is between 0 and 2, so in the pushed wave case. Because if we plot the drift term as a function of x, so if we plot gamma plus 2 grad g over g, then as x goes to minus infinity, then this drift term goes to gamma, which is positive. And as x goes to plus infinity, then it goes to gamma minus 2, which is negative if gamma is between 0 and 2. So that means that the drift is negative when the diffusion is a long way to the right of the origin, and it's positive when it's a long way to the left of the origin. So the diffusion always has a drift towards the origin when it's a long way from the origin. So it ends up having a stationary distribution. And it actually has a nice explicit density, which is given by pi of x is g of x squared times e to the gamma x, and then normalized. So it turns out that the exact condition for this diffusion to have a stationary distribution is for to be in the pushed wave case of gamma being between 0 and 2. So what this suggests should happen is that, so if we run our population model for a long time, and then we sample a type capital A individual from close to the front, and we trace its ancestry backwards in time for a long time, then its location relative to the front at that earlier time should have a distribution that's roughly given by this density. So in particular, it should be very likely to be in this yellow region of being relatively close to the front. And we can rigorously prove this in the case where, in the bistable case of gamma between 0 and 1. So that's what happens for a single ancestral lineage. So finally, I just want to, I guess I just about have time to tell you about what happens for multiple ancestral lineages. Now what we want to do is take multiple type capital A individuals and trace their ancestry backwards in time, and get the coalescent process that we get where ancestral lineages merge when they have a common ancestor. So because of the way that our model is defined, then ancestral lineages can only coalesce when they're distance at most 1 apart. And that's because they can only coalesce when one is the offspring of the other in a reproduction event. So that means that when we do our space scaling of 1 over n, then ancestral lineages have to be extremely close to each other to coalesce. And let's suppose that we have 2 type capital A ancestral lineages at some site y at time t. Well, what's the rate that they coalesce? Well, they're each being hit by reproduction events at some constant rate. And when one is hit by a reproduction event, then the probability that the lineages coalesce is the probability that it was the offspring of the other one in the reproduction event. And that probability is 1 over the number of type capital A individuals at y at that time, which is proportional to 1 over pnt of y. So now if we take a location X relative to the position of the random traveling front, after doing our space rescaling, what's the rate at which we should expect to see coalescence at X? Well, we would have something that's proportional to roughly pi of x squared, which comes from the probability that two ancestral lineages are very close to X, and then divided by g of x, which comes from the rate at which two ancestral lineages at X coalesce because of this. And if we plug in what pi of x is, then we get that this is g of x cubed times e to the 2 gamma x divided by a constant. And because g of x goes like e to the x e to the minus x as x goes to infinity, then this goes like a constant times e to the 2 gamma minus 3 times x. So now we've got two different cases. So if gamma is between 0 and 3/2, then 2 gamma minus 3 is negative, which means that this thing goes to 0 as x goes to infinity. So that suggests that the rate of coalescence out here in the tip is very low, and so all of the coalescence is going to happen, is likely to happen in this orange region here, so relatively close to the front. And that suggests that what we should see under a suitable time rescaling is a Kingman coalescent. And that's because, at least if you're in this orange region, then the rate at which coalescence happens is much slower than the rate at which ancestral lineages move around. And so once a coalescence event has happened, then the ancestral lineages have time to get back to their stationary distribution before any more coalescence is likely to happen. So what's sort of, at least the heuristic suggests here, is that the selection and the spatial structure in the model create this speed and shape of traveling wave that creates the motion of the ancestral lineages and their stationary distribution, which in turn means that the coalescent that you get is actually the neutral coalescent that you would expect from a neutral population with no spatial structure, the Kingman coalescent. But instead, the other case is if gamma is between 3/2 and 2, in which case 2 gamma minus 3 is positive. So this thing blows up as x goes to infinity. And so that suggests that the highest rate of coalescence is out here in the tip in this orange region, even though most of the time, most of the ancestral lineages are in this region. And that suggests that what we might see is under a suitable time rescaling is a coalescent with multiple mergers. So a coalescent in which multiple lineages can all coalesce together at the same time, unlike the Kingman coalescent where mergers are only pairwise. And that's because if a lineage manages to get out into the tip and coalesces with another lineage, then it's fairly likely to coalesce again relatively quickly. And so under the time rescaling, it might look like the multiple lineages coalesce simultaneously. So this fits with a recent non-rigorous physics paper of Birzu, Halacek, and Korolev, where they looked at the PD that we saw as our scaling limit with some noise added to it, and said that the effect of the noise was different for gamma between 3/2 and 2 compared to gamma less than 3/2, and suggested that this case should be called semi-pushed rather than pushed. So these are all just heuristics. So what can we actually say rigorously? So for now, again, we can only prove things in the bistable case where gamma is between 0 and 1. So in that case, if capital N is much bigger than n cubed, then we can say that if you sample k type capital A individuals from near the front, then the times at which their ancestral lineages coalesce after rescaling time by little n over capital N are approximately given by a Kingman coalescent. And I think I've overrun a bit, and I'm sorry about all the technical issues, but thank you for listening.
Thank you, Sarah, for your talk. Do we have any questions? So if not, in the...
Sorry, actually, I have a question.
Okay.
Thanks, Sarah. That was really interesting. I have a question that maybe is a little bit outside of what you have done, but in the case when gamma is less than 1, you know, you've got a great description of what happens once a wave is gotten going, but this is a really troubling case from a biological standpoint because the heterozygote is less fit than either homozygote. So the idea that there would ever be, you know, enough big A's around when, say, a first few mutants get introduced, the idea that it would get to this wave situation seems a little hard to get to. So I wonder if you've thought about that a little bit at all, or what you might say about it.
Yeah, I mean, so I guess the idea would be that it would arise in the same way that a hybrid zone can arise, where there have been, so in the past, populations separated by some kind of barrier, right? So there are situations, in plenty of situations, where hybrid zones have arisen in biology.
Certainly, yeah, that's a great situation, an idea. I also think it would be interesting, to look at the stochastics of how, one could potentially get to a big A allele invading a population if it somehow got to higher frequency. And then I think it would be a very different story if you look at the coalescent process that traced back, to the origin of that sort of thing, as in a kind of a selective sweep.
Yeah, so are you saying how so I guess, yeah, so in what we've done, we've always got a long way to the right, you've got all type capital A, and a long way to the left, you've, well, one way or the other, you've got a big pool of each of them. So you're suggesting sort of one of them arising from mutation or something, and then spreading.
Okay, there are two more questions in the chat. I don't know, do you see the chat, Sarah?
Yes.
So one from Matthias Birkner, who's asking about an intuition why capital N should be much louder than small.
Yes. That's a good question. So I think it's a technical assumption rather than one that's maybe strictly necessary. So yeah, so I can't give you a short intuitive reason why we need it in the proof, but I think it's, at least to an extent, just a technical assumption.
And then another one by Emmanuel.
Yeah, so gamma being bigger than 1 means that you're no longer in a bistable regime. So that just makes it a lot harder, because so the growth rate in the tip is positive. So it's not positive enough to make it a pulled wave, but it's still positive. So if you have a little bit of noise out in the tip, then that could, well, it's just harder to control, because if gamma is less than 1, then a sort of small amount of noise will just end up going away, and you can control it quite easily. But for gamma bigger than 1, then you have to work a bit harder.